comparison to traditional control will replace a lot of PID loops, and then it will just, so if you read here, it's a global steady state optimizer at the top, then you have a local steady state optimizer, then you have dynamic optimization through MPC, using your using your decision variables the best possible way dynamically to achieve some dynamic objectives, and then you have lower level PIDs doing the work instructed by MPC. Now, what are the benefits of MPC? Well, MPC, no one tries to replace their old functioning system with something new unless they have something really big to achieve. And MPC does offer something called multivariable control. If you have mismatch in the number of inputs and number of outputs, and you don't know how to couple them, and there are severe couplings, you affect one input and it affects 5 outputs. So you cannot have direct couplings between each input and the output. That's where MPC helps significantly, because it does something in an optimized way, which as a human we cannot just think like how to use, which one to use the best, which input to use with which output. So it does it in a much more rigorous, much more methodical way. And it has an inherent feed forward, like the grumpy wife example. You know it hours before that she's going to get grumpy, so you can act against it. At the same time, you have something also very important is output constraint handling, which is very important in problems like refinery, where you have a specific specification of your diesel, and you have to meet that, and that is an output, that so much propane has to be there or whatever. So you have to meet those constraints, and with traditional PID it is a bit hard to do. So that's where it also contributes, where you can predict what specification you want to produce and you act already accordingly ahead in time. But there are disadvantages of MPC. You have to measure the disturbances. It takes disturbances as a feed, without which it cannot act. And also that the MPC runs an optimization, so it's an additional computational load. Now, to address the main topic of this trial lecture is the comparison between model-free and model-based control. I presented some model-free methods like PIDs, and I presented some model-based control like MPCs. And here is an example from Japan, where I show the application of process control in a specific chemical plant. And here you can see over 5,000 PID applications, whereas only 50 for linear MPC. And linear MPC is also something very important, because it's the most used MPC. Very rare applications of non-linear MPC, as you can see, just 2 of them. So linear MPC is the MPC that is most preferred in the industry. But here it shows the difference between the number of applications. As I went into this lecture by Benjamin Recht in a machine learning conference, and he talks that 2 parameters, and he's talking about PID parameters, P and I, suffice for 95% of all control applications. So then we are actually aiming for very, very small, just 5% of the applications where something else could be useful. So in the bigger picture of control applications, we have 95% applications that are in PID domain, and then the rest 5% are non-PID. And in this non-PID, we have 95% again as MPC. So we are aiming at only 5% that is remaining in the traditional control domain to have an influence from something else, like a modern, machine learning based control. So we need to do a cost-benefit analysis to talk anything or make the comparison between the model-free and model-based control. So the cost is clearly that the model-based control has a expensive infrastructure. You need to have a new software or software connection with your hardware and actuation, as well as optimizer running all the time. But if there is a lot to gain, it is perhaps necessary to change from PID to model-based control, and it is probable. But the PID's real problem is tuning, which can be addressed by intelligent PID solutions, which are still model-free, and it can also be addressed using model-free reinforcement learning, which is definitely an option, but it could be an overkill, but only the time can show what it has. However, PID is known to function very badly in severely nonlinear systems, and there model-based control could definitely help, but it is again a rare case. Where model-based control is making a real big influence is in the area of refining, which is here. As I already talked about, these specifications that you have of these end products, they have to be met. If they are not met, you cannot sell them at the same price, or you can't even sell them at all. Polymers, they look like this. I worked in a petrochemical company where you produce these pellets, and these pellets have to be having perfectly defined specifications, something like polymer index and so on, which you have to meet those things. So there are very, very huge losses if you don't meet those criteria. So there is something huge to gain or way too much to lose if you don't use model-based control. Oil production, where you have gas being injected and then you have lower hydrostatic pressure in the line and a lower back pressure, which increases production. Oil, more money, money driven. And airplane control, I need not to talk about that. Then there is robotics, which is a very difficult problem, a lot of things happening there, where MPC or model-based control is very useful. Whereas if you look at wastewater treatment, not much is going on, nobody cares. So people are happy with feed-forward or some basic PID control. But one question that wondered me a lot is, if live testing is needed to be done on simulators, which are essentially models, how can a model-free controller be truly called model-free? And I don't really have an answer to it. Will machine learning take over? To the bigger question, well, machine learning came from computer games, as has been shown in AlphaGo example. And the one thing that is very noteworthy is that in a game setup, the quantification of value is very clear. You have a score going on, and if it is increasing, that's a positive. If it is decreasing, it's a negative, or your opponent is getting a point, that's negative. So the quantification of value is very, very easy, and these processes are extremely deterministic. So machine learning has the specific niche in these kind of applications, but we need to see how it will do in other applications. How it will react with stochasticity for that matter. It is also popular in robot control. Drone control in particular is very popular. But one thing is to note is that in all these systems, there is a very little risk of failure. If your robot doesn't go off and doesn't fly itself, there is no problem. If you lose a game, nothing much to lose. You can learn from it and you can do it better, which is what AlphaGo did. So the live testing of the concept is easy in certain applications, which is probably not the case in your oil field production or in your process plant, where you have a lot of things going on, and if the pressure hits this and that, and so you get it. Evolutionary algorithms, which is part of machine learning, are conducive to systems that are highly nonlinear, stochastic, and poorly understood and difficult to solve using conventional methods, which has been picked from this paper back in 2002. So, machine learning can handle highly nonlinear problems, high-dimensional difficult control problems like autonomous car, computer vision, robot control. These are things we could not address. These are problems we could not address with traditional control, no matter how. You cannot expect to show 1,000 pictures and then expect a model which just predicts that it's a cat or it's a human or so on. Which, by the way, is very, very important in autonomous driving context. Because if you can detect a human walking on the street, you have to stop, and so on. So, machine learning can definitely improve the current technology, can take over some of the model-based control applications like MPCs, as I talked about. It's linear MPCs that are often used in industry, and they are prone to maintenance because you have to relearn your system or re-identify your system after some time because some disturbances or some changes in the process has changed it, which is always the problem with maintaining MPCs, where machine learning can add some adaptive capabilities. So it might be inherently adaptive to those things, and it relearns by itself that now it has to do things differently. There is a nice paper with the comparison of machine model predictive control and reinforcement learning, where it concludes that reinforcement learning is competitive with model predictive control, even if a good deterministic system model is available. So that's a very concrete result, and this is a 2009 paper. Uptake of machine learning depends on conservativeness of the field, like robot control or drone control. It's not a big deal, but process control is a big deal, where you don't want a machine to be learning on the go and controlling it. So conservativeness is a bit of an issue, trial and error fear, and live testing possibilities. However, there is one more issue that I see is correlation, is not causality. Let's say there is a correlation between raining in London and New York buying umbrellas. Does that mean that if it finds that the New York is buying umbrella, it will say, now it is 100% sure that London is going to rain? So it's not causality, but there is correlation. So machine learning systems have to be smart enough to figure that out themselves. As well as uncertainty handling is a big challenge. Now we need to look or address machine learning's takeover question on emerging industries. So medical marijuana. Control is definitely needed in this field, but not of artificial intelligence type. Probably regular intelligence will work, but more to other more serious emerging industries. Green energy. We have a huge problem in demand-supply mismatch. The demand and the supply, I mean, supply is always with green energy uncertain. How many windmills to, or how many wind power is uncertain, solar power is uncertain. So now machine learning is trying to make very predictive models which are very accurate, and that's where machine learning is definitely going to help to minimize the gap between demand and supply. And also learning how people use energy, what time of the day they use energy, etc. Then we have drones control, autonomous cars, and drug discovery is another very, very big, because it takes 12 years to, on an average, to produce a drug, and I guess we lose a lot of people during that time. Machine learning is scalable. It is the same algorithm. You throw it to any problem, and it just finds out these parameters I talk about, and that's it. The key drivers in this field of success for machine learning is cloud computing. Now you don't have to have your own data centers. Google, Amazon, they offer cloud computing services. You just need to have connectivity to the internet. It produces what you want. So it takes away your computing load. The use of IoT devices, Internet of Things, your devices are smart. They have wireless connectivity. So they just talk to the cloud computing directly without having to have a direct sensor right there connected on a wired way. Then you have parallel computing coming along with NVIDIA graphic processing units. These are recent advances which has really uplifted machine learning, but there is again a huge threat of cybersecurity. Let's say all of your production data, everything you're running an oil field is out there on the internet. Someone can hack it, and someone can then say, you don't get back your control without paying me so many thousand million kroners. So that's again a challenge which machine learning has to take over. So though it comes from cybersecurity, which is a different field. But there is something called